Thank you very much for the invitation, for the opportunity to speak. So this is a joint work with Tristan Bozec and Damien Calaque that I will present here. So it's basically, we divided this talk into two. So I will cover more the theoretical background, and then Tristan on Thursday will focus more on the application in geometric representation theory. Okay, so to the structure of my talk. So in the first part of my talk, I will first talk about symplectic and Lagrangian varieties, just a fast overview. And then in the second part, I will explain how we can, how symplectic geometry has been extended to the derived algebraic geometry setting. In the third part of the talk, I will talk first about something seems completely different, about a Calabi-Yau completion of DG categories. And then finally, in the last part of my talk, it will all come together. I will introduce moduli spaces of perfect complexes and show what Calabi-Yau completions have to do with derived symplectic geometry. Okay, so let me start with what a symplectic and Lagrangian varieties are. So if we take, for instance, X to be a smooth variety over a field, let's say of characteristic 0, and we denote T of X the tangent sheaf and L of X the cotangent sheaf over X, then we say that the space, the variety X endowed with a closed two form. So closed two form is a global section in the second wedge product of the cotangent sheaf. We say that this space is symplectic if this form is non-degenerate. So what does it mean to be non-degenerate? Well, if we have such a two form, then this two form always induces a morphism from the tangent sheaf to the cotangent sheaf. And we say that X is symplectic if this morphism that is induced is actually an isomorphism. So if we have a symplectic space X, together with a symplectic form omega, then we can also define what a Lagrangian subspace is. And so this is a closed embedding, it's an embedding of a closed, smooth and closed subvariety of X, so Y into X. And we call Y a Lagrangian subspace if the following sequence is an exact sequence. So we can go first from the tangent sheaf of Y to the pullback of the tangent sheaf of X. Now we use the fact that X is symplectic, so we have an isomorphism between T of X and L of X, so also between the pullbacks, of course, and we always get, of course, a morphism from the pullback of the cotangent sheaf on X to the cotangent sheaf on Y. And if this composition is an exact sequence in perf Y, perfect complexes over Y, then we say that Y is a Lagrangian subspace. So this could also have been said maybe in a slightly easier way. So the usual definition of a Lagrangian subspace would rather be that Y is a smooth and closed half-dimensional subspace of X, such that if I evaluate the two form on Y, this form vanishes. So this is equivalent to what I wrote here, where the vanishing condition is given by the fact that this composition of these two errors is 0. And the fact that it's exact, it gives me the half-dimensional condition. But we'll see, I mean, we'll understand in the second part, when it comes to the derived setting, why it makes sense here to define a Lagrangian subspace in this way. Okay, let's maybe view some examples. So every cotangent space of a smooth variety is naturally endowed with a symplectic form. So it's a symplectic variety. And if I take the 0 section, so Y into T star of Y, then this makes Y a Lagrangian subspace. Another example that Tristan is also going to talk more about are Nakajima quiver varieties. So these are quotients of cotangent spaces of representations of quivers. And they inherit symplectic form from the cotangent space structure. So yeah, let's just review maybe the easiest example. If Y is equal to C, then I can look at the cotangent bundle, which is isomorphic to C star. And this carries a Liouville 1 form, so Y times D of X. And if I want to obtain the symplectic form, so the 2 form, all I do is I apply the differential to it, and then I obtain the 2 form d of y wedge d of x, and that will induce a non-degenerate 2 form onto the tangent space. So we'll also see later on that this can be done in a much more general context. Okay, so let us move on to the derived setting. So we're going to work with derived stacks. So what are derived stacks? So there are functors from the category of commutative differential graded algebras whose cohomology is concentrated in non-positive degree. And they're functors to the category of spaces, of topological spaces, and they're functors which satisfy étale descent conditions. Here in this talk, I will denote D stack, the category of derived stack, and just stacks, the category of normal, ordinary, underived stacks. And so what I always have is I, of course, always have a natural embedding of stacks into derived stacks. And this embedding comes with a right adjoint, which is called the zero truncation. So I can produce out of a derived stack by truncation an ordinary stack. Let's maybe view this on an example. So for instance, if B is a commutative differential graded algebra, then I can define a derived stack, which is in this case actually a derived scheme. It's called R spec of B, and it is simply the functor which maps an algebra A, so a commutative differential graded algebra A, to the space of algebra maps between B and A. And that's a derived scheme, and the truncation functor does what we expect it to do. So if we take the truncation of this derived scheme, then what we obtain is an ordinary scheme, and it's just a spec of H0 of B. So the zeroth cohomology of B is a commutative algebra, and I can just consider classically its scheme. So this is the setting where we'll be working in. So in terms of notation, we can, we're not gonna consider only the tangent sheaf and the cotangent sheaf, but more generally the tangent complex and the cotangent complex of a derived Artin stack. And so we will assume also, I already said it, that X is an Artin stack, which is just a technical condition that implies actually that this complexes that we have, so L of X is a perfect complex over X. So if X is an underived scheme, then taking the zero truncation of the cotangent complex and the tangent complex would just give me the ordinary tangent sheaf and cotangent sheaf respectively. If we have, if X is a smooth and underived scheme, then I also know that it is known that the cotangent complex actually has its cohomology concentrated in degree 0, which means that it's isomorphic to the cotangent sheaf, and the same is true for the tangent complex. So the tangent complex is also just concentrated, has cohomology concentrated in degree 0, and it's just this equivalent to the tangent sheaf. So we haven't really gained any more information for smooth underived schemes. Okay, so Pantev, Thurn, Vakir, and Vezzosi have in 2013 extended first the definition of what a P form is, and here, unlike in the normal and the underived setting, we can talk of P forms with a degree. So we can define P forms of degree n on X. And what are these? These are global sections of a certain algebra of sheaves. We take the symmetric, the pth symmetric power over O of X of the cotangent sheaf, of the cotangent complex, not the cotangent sheaf, shifted by -1. And this complex is shifted then by n plus p, where n is the degree and p is the form. So you can see if you plug in now a 2 and then you get and n equal to 0, then you get exactly what the underived 2 form is. If you set in general n equal to 0, you will get the general definition of a P form. So we call and I mean exactly like in the underived setting, if I have a two form, this will give me a morphism between the tangent complex and the cotangent complex, but now shifted in degree n, because we have this additional shift here. And exactly like in the classical setting, we would say that the two form is non-degenerate if the morphism that is induced by the two form is actually an isomorphism. So an isomorphism between the cotangent, the tangent complex and the cotangent complex with a shift by n. Okay, let's go to the definition now of shifted symplectic structures. So also in the same paper by Pantefto and Baquier and Bezzosi. So this is really exactly dual than in a classical case. So we call a space X with a closed two form. Now we have to specify the degree. So of degree n is called n-shifted symplectic if this two form of degree n is non-degenerate. So if it induces an isomorphism between the cotangent and the tangent complex, where we allow a shift by n on the cotangent complex. More generally, now there's a concept that's been introduced, is the one of not only of Lagrangian maps, but also of a correspondence of derived stacks being n-shifted symplectic. So what does it mean for correspondence? First of all, what is the correspondence? Correspondence is just a diagram as you can see it here. So you have a map from X to Y and from the same X to Z of derived stacks. And we will say that it is n-shifted Lagrangian if there exist non-degenerate closed two forms of degree n on the outside, so on Y and on Z, and such that the diagram that we see here commutes. So remember beforehand we have, if we have a map from X to Y, then we have a map between the cotangent, the tangent sheaf, the tangent complex on X to the pullback of the tangent complex on Y. Now the non-degeneracy of the form gives us an isomorphism to the pullback of the cotangent complex on Y, shifted by n this time because it's a degree n form. And we obtain now, we always have a map from the pullback of the cotangent complex of Y shifted by n to the cotangent complex of X shifted by n. So we can do the same thing for the, I mean, we can consider these two maps for the bottom part of the diagram, and for the top part of the diagram, we can do exactly the same. And now we pose the condition that this diagram is co-Cartesian. So there are actually two conditions hidden in there. First of all, of course, that it's a commutative diagram, which means basically that these two forms, omega of Y and omega of Z, pulled back to X, have to be equivalent. And we want the diagram to be co-Cartesian, which is a form of non-degeneracy condition. Okay, we can also then say what it means for a map to be n-shifted Lagrangian. So not beforehand, we defined a Lagrangian subspace as a half-dimensional subspace on which the form vanishes of a shifted symplectic space. And here we will just use the definition of correspondence. So we say that a map is n-shifted Lagrangian if the correspondence, where now we take the map from X to Y, but we project X on the left-hand side to the point, is an n-shifted Lagrangian correspondence. So if you go now back to the diagram, that means that, for instance, Z is just the point. So in the upper corner of the diagram, I will just get the zero sheaf. And this means that the bottom part of the diagram is actually a fiber sequence, or if you prefer, distinguished triangle. So, and if you set n equal to 0, then of course you see that this is exactly the way we defined a Lagrangian subspace in the classical setting. So it is just a general, I mean, it is a natural generalization of what a Lagrangian subspace is to consider shifted Lagrangian maps. Okay, let's also view some examples on this. So First of all, well, like we said at the beginning of the chapter, every symplectic, every ordinary stack can be seen as a derived stack. So every symplectic variety is also, of course, a derived stack, and it will naturally be zero-shifted symplectic. The reason for this is what the remark we mentioned here. We know that if X is a smooth underived scheme, then its cotangent complex is just equivalent to its tangent sheaf, and its tangent complex is equivalent to its isomorphic to its tangent sheaf. And that means that the condition of being zero shifted symplectic is exactly the same than of being classically symplectic, and the same for Lagrangian. So obviously then the classical, this is exactly as we expect it to be, the classical picture should be examples of zero shifted symplectic structures, and every closed subspace should yield a zero shifted Lagrangian map. Of course, we cannot expect anything else, because we know that the tangent complex and the cotangent complex are both only have cohomology in degree 0. So it couldn't be anything else but zero shifted symplectic in any case. Okay, so the problem that Tristan is going to address in his talk is, so we know that classical symplectic varieties give zero shifted symplectic structures, but we could also wonder the other way around. If we have a derived space or non-derived space, and we have some shifted symplectic structure on it, or a Lagrangian map, can we use this in some way to obtain a classically symplectic or Lagrangian structures? So I won't talk about this in this talk. This is what Tristan's going to be addressing. To name some examples that are really parallel to the classical ones, we can, in the derived setting, also define a cotangent space. And here we can even more generally define what an n-shifted cotangent space is over a space, a derived stack Y. And it's just defined as derived spec of sim of the tangent complex shifted by n. So this is a relative spec over Y. And we know that this n-shifted cotangent space is n-shifted symplectic. Exactly like in the classical case, the zero section of this map. So we have a zero section from Y to the n-shifted cotangent space shifted by n, which is just given by projecting sim of ty of n onto the first factor. And this map, this zero section becomes an n-shifted Lagrangian map. More generally, that's the third point. If I have in general a map from Y to X, then I will always get an n-shifted Lagrangian correspondence, which is the one that is written here. So in the middle, we find the n-shifted cotangent space of X pulled back to Y, and we have maps, natural maps to the cotangent space of Y n-shifted and to the cotangent space of X. And one can show that this is in general an n-shifted Lagrangian map correspondence. And of course, if now I was to put X equal to the point, then you can see that this is just a generalization of the second point, because I obtain just the zero section and the projection from Y to the point. So it's a more general statement. Let us to make the parallel with the Louisville form construction that we've seen on the first slide. Let me maybe repeat how, let me give you a sketch of how we get the two form. It's not very difficult. The difficulty is more, of course, as usual, showing that this two form indeed is non-degenerate. So this cotangent space, the shifted cotangent space, has the following property. So every map to the cotangent space is given by two sets of data. So the first one is a map of derived stacks from Y to X, and the second one is a global section in the pullback of the cotangent space, the cotangent complex of X shifted by N. So pulled back along the first map F. So if I was to apply this to the identity map, so I replace now y with t star n of x, so with the cotangent space, and I just look at the identity map, then I first get a map F that is the projection of the cotangent space, nth shifted cotangent space onto x, and a section that I call L of x of the pullback of the cotangent space of x and shifted by F. So this is just the recipe from above applied to the identity map, and it will give us a section which I call L of x. So now, I mean, there are a few steps that are not very complicated. We have, of course, always a map along, I mean, we have this map F, and we can look at the pullback of L of x of the cotangent complex along this map, and it will give us a map to the cotangent complex of the shifted cotangent space. And we can just look what happens to L of x under this map. So we get a global section of the cotangent complex of the cotangent complex of the cotangent space shifted by n. So this is a one form by definition. It's a one form of degree n, and it is exactly what we what the Louisville form is on the first slide. So to obtain a non-degenerate form, all we need to do is take the differential of this. So if we take the differential, it will give us a two form of degree n, and this two form is clearly closed because it comes from it's the image of a one form. And the difficulty is now to show indeed that this is in this setting a non-degenerate form. Okay, so that's the major example of a shifted symplectic space. And now in the next section, what I would like to talk about is DG categories. So we'll make a cut and talk about n Calabi-Yau completions of DG categories. And then we will go back to the n-shifted symplectic structures and make the connection between these two concepts. Okay, so if we have, let me just recall, if A is, we will take A to be a k-linear DG category. So this is just a category.
Very soon would be a good moment to make the 5-minute break. You can choose when is a good time.
Yeah, I saw that it didn't really fit with the time, but I think in terms of content, it would be perfect. Yeah. Let's make the 5 minutes break now, I think. Yeah.
Sounds good.
So I'm going to allow everyone in the audience to unmute themselves in case they wish to, so that they can ask questions.
So you have shifted forms and non-shifted forms. Is there a way to, by pullback, to pass between shifted and unshifted in some cases?
I mean, zero shifted forms are just the classical forms, actually.
Right. But if you pull back it to something crazy, it stays non-shifted.
It stays. I mean, it's a shifted form. No, the problem is, for instance, if you have an, I don't know if that's what you mean. If you have, for instance, an underived space, it can still be n-shifted symplectic. Okay. And then you could wonder if you have a Lagrangian, n-shifted Lagrangian map, what kind of property does it have in a classical word after you apply truncation to it? And in general, that doesn't quite fit. I mean, you can't, I mean, it's not going to be something that makes sense in the classical setting. No, it's not what you mean.
I mean, can you change this number shift by any?
No, I mean, it's an isomorphism.
Is that what the problem was?
And the cotangent complex. So, I mean, if T of x is isomorphic to L of x n, then it cannot be isomorphic to L of x n plus 1, let's say. So, not really.
I think the question is more about forms in general, not necessarily symplectic forms.
Yeah.
Right? It's saying like if you have an n-shifted,
you have, for instance, a two form, then it will induce this isom. I mean, it will. Yeah. Okay. But forms.
I guess it's probably just it retains the shift.
The question is about the degree of a cohomology class, and the degree of a cohomology class doesn't change under pullback. That's, I think, the quickest answer to the question.
Nor the shift.
But well, in this Liouville form construction, it looked like you just.
Yeah, okay, you can of course pull it back. If you have a map from X to Y, you can pull back the form but yeah, okay, I understand what you mean. It will of course not be then on the pullback something that necessarily is non-degenerate or so.
Some other operation, I don't know, not like some kind of tone maps that can change degree.
Yeah.
Is this what Tristan will be talking about?
I haven't seen any example of that kind. I mean,
okay, thank you.
Is this what Tristan will be talking about in his talk?
well, he will talk about an application of what I'm talking about, so of end-shifted symplectic structures to really construct classical Lagrangians of symplectic of symplectic varieties. Yes. So to a certain extent, yeah.
Cool. Should we get started again?
Okay. So I have how much time left?
25 minutes.
25 minutes, okay. Okay, so let me share the screen again. I will put it on slideshows. Okay, so we're going now to talk about something quite different, about the DG categories and their Calabi-Yau completions. So, sorry, I'm not used to use preview as a, so I tend to, yeah, with the mouse unslide my slides. Okay, so we take, we're going to look at K-linear DG categories. So this is just a category with objects, and the morphisms are complexes of K modules. We'll denote mod K, the DG category of complexes of K. By mod A, we will denote the DG functors.
Can you share your slides, please? We still see your, we like seeing your face, we like to see your slides.
Sorry, yeah, I indeed did forget to, 1 second. Yeah, share. Does it work now?
Yes.
Perfect. Yeah.
Good. Okay. Yeah, it's written actually here. You share your screen. Okay, so we have like I said, we're going to look at K-linear DG categories. So morphisms are complexes of K modules. Mod K will denote the DG category of complexes of K modules. Mod A will be the DG category of DG functors from A to mod K. So functors that respect the complex, the structure of the Helms as complexes. We can also, in the setting of DG category, take the tensor product of two DG categories. So I will denote AE. It's like in the setting of commutative algebras, we can take the tensor product of two DG categories, so of A tensor A up, and I will define the module in this. So this. If I look at the category of AE modules, that's just the category of A bimodules. So I can view A as an A bimodule with an action on the right and on the left. I can look at the internal Helm in mod A of A, comma AE, and I call this the inverse dualizing complex. And this will naturally be also a module in AE. So we call definition, and we call A smooth if A is perfect as an AE module. So if that's exactly the same definition that you know maybe from algebras, and we call A n Calabiyau if there is an isomorphism of AE modules between this dualizing complex shifted by n and A itself. So both are AE modules, and I ask, I mean, if there are n Calabiyau, if I have this and if I can find an isomorphism between them, which is an isomorphism of A bimodules. Okay, one remark. So no, that's not what I wanted to do. We can, if we have a morphism between the dualizing complex shifted by n and A is, we assume that A is smooth, then this is the same then is equivalent to taking the derived tensor product between A shifted by n and AE, and A over as an A bimodule. And this is exactly how Hochschild homology of A shifted by N is defined. So we can identify a Calabiyau structure, or we can view a Calabiyau structure as an nth Hochschild, as an element in the nth Hochschild homology ring of A. And another remark is that, so this bimodule A, this inverse dualizing complex, also defines a functor from mod A to mod A, where I just take an A module and tensor it over A with this dualizing complex, which is an A bimodule. And this gives me a new A module, and this is exactly the Serre functor. So, in fact, we call this means that mod A is if A is n Calabiyau, then the Serre functor in mod A is isomorphic to the identity functor, because tensoring with A is just exactly the identity, and shifted by n. So it means that the Serre functor is the n shift in mod A. Okay, some simple examples. So if I have a smooth variety, then I can look at the perfect complexes over X. This category has the DG enhancement, and this category will then also be a smooth DG category. If X is a Calabi-Yau variety of dimension n, then the DG enhancement of the perfect complexes of X is n Calabi-Yau. Also what we will do later on is we're going to consider a quiver as a DG category. So we can just consider its vertices as objects, and its morphisms are the K-linear combinations of paths between them. So you can also, if you want, give a grading to the errors, and then you don't only get a DG category that is concentrated in degree 0. Okay, so Keller has defined, so if I have a DG category and an A bimodule, let's call it M, then what we can consider is the free tensor DG category of M. So this is given as follows. So TA of M is the sum of A plus M tensor M over AE, so as A bimodule, plus and so on. So this is all derived, but I mean, if you choose a fibrant model of M, then you can just get rid of the derived sign here. So you have an infinite sum of always bigger tensor powers of M. So this is a category whose objects are the objects of A, and the morphisms are given by this sum of tensor products of M's. So like how we can also explain, I mean, a conceptual way to explain this functor is, well, TA blank is a functor from the A bimodules to DG categories with functor from A to this DG categories, so DG categories over A. And it's actually the adjoint to a functor that sends every, so a map between DG categories. So if I have a map F from A to B, so DG category over A, then I can produce out of this an AE bimodule just by sending the pair A prime to the complex HOM in B of FA prime comma FA. So FA prime is going to be an element in B, and FA is also going to be an element in B, and now I can just look at the HOM space in B, which is a complex. So that defines me an AE module. And this construction of the free tensor DG category is the adjoint of producing a bimodule out of a morphism from A to B. So this construction can be used to produce, to do the following. So if we have a DG category, and this DG category is not Calabi-Yau, then there's a way to make it Calabiyau, I mean, to produce a Calabiyau category out of it, and it's called the n Calabiyau completion of A. So we take, we define the n Calabiyau completion of A to be the free tensor DG category of A, and as bimodule, we take the Serre functor, so the inverse dualizing complex shifted by n minus 1. We can also have a deformation of that construction. So if we take C, for instance, just an A bimodule map from this dualizing complex to A, then this will define a functor between TA of C, between between the n Calabi-Yau completion of A and A, because all I need to tell you on this free construction is A is mapped to A, and the A and C tells you exactly what to do with this A bimodule. And now what we can do is we can look at a homotopy push out. So we have maps from the Calabi-Yau completion. So one map is induced by C to A, and one is induced by 0. So the one induced by 0 is just the projection onto the first factor, onto the first summand, so A on A, and A dualizing complex goes to 0. And we can take the homotopy push out of this. And this is called the n Calabi-Yau completion, the n+1 deformed Calabi-Yau completion, and it depends on this map C. So what has been shown by Yeung, Keller, and also by us under different assumptions, so the strongest, I think, being A being a smooth DG category, is that if for every negative cyclic lift of C, C I wrote beforehand as a map from A dualizing complex shifted by n-1 to A, but as I explained, it's also the same thing in the class in the Hochschild homology. Induces an n+1 Calabi-Yau structure on the deformed Calabi-Yau completion. So this means that if C is equal to 0, as it is in the first case, so if I look at the undeformed Calabi-Yau completion, we always have a negative cyclic lift of 0. So this is always, we always have an n Calabi-Yau structure. But in the deformed case, Yeung has actually shown, has given an example where we don't have such a cyclic lift. And indeed, he constructs an example where the Calabi-Yau, the deformed Calabi-Yau completion is not Calabi-Yau. So, I mean, it seems to be a necessary condition to assume, it seems necessary to assume that there is a negative cyclic lift of C. Then let's make a remark. So important, this Calabi-Yau completion have also appeared beforehand. So as examples, for instance, if I take A to be the DG category KQ, a Q quiver, and I take W, a class in the Hochschild, zeroth Hochschild homology, Hochschild homology ring of KQ. So this is just a sum, the zeroth Hochschild homology ring of KQ is just a sum of cycles in Q, modulo cyclic shifting. Then Ginzburg has defined the Ginzburg DG algebra, and that turns out to be nothing else but the 3 Calabi-Yau completion of the differential of W and KQ. So that's let me just for the context say that's a very important construction and has many applications, for instance, in the categorification of cluster algebras, where I look at a quotient of perfect complexes of this DG of this Ginzburg DG algebra. So let's maybe view an example. So I've chosen a very, the simplest non-trivial example. If Q is A2, so in this case, there are no cycles, so the potential W has to be equal to 0. And in this case, the Ginzburg DG algebra looks as follows. So we have a DG quiver, so a DG quiver path algebra. So we start off with the quiver A2. Then the recipe is the following: we double all the arrows, but invert their orientation. So for an arrow alpha, I get an arrow alpha star. And for every loop, in every vertex, I add a loop of degree -2. I add first a loop. So the degrees are as follows. So the quiver on the right is a quiver that is not in degree 0, but in different degrees. So degree 0 will be all the arrows and vertices from the original quiver. Then we have generators which are in degree -1, which are the arrows that I have inverted. And we have generators in degree -2, which are the loops that I have added in every vertex. And in this case, because we chose W to be equal to 0, there are only on the generators 2 non-zero differentials, which is a non-zero differential T1 and one on T2. So that's an example of what the DG Ginzburg DG algebra looks like for A2. So there's also we've seen beforehand the definition of a shifted Lagrangian structure for a correspondence of stacks. So now the equivalent, and we will just see in a second why it's really the equivalent, is the definition of Graf and Dickerhoff of an n Calabi-Yau cospan. So if I have a cospan is what you see here. So we have maps between DG categories, one from A to C and one from B to C. And then we call this cospan n Calabiyau. So again, as if on the outside part, we have non-degenerate Calabiyau structures, eta R and eta beta, that make A and B n Calabiyau. And we have a homotopy. We want the following square to be a homotopy, a co-Cartesian in bimodules over C. So we have a map from the inverse to, so taking the inverse dualizing complex is contravariant. So we get a map from the n-shifted inverse dualizing complex to the inverse dualizing complex of A and the inverse dualizing complex of B, but induced up as C bimodule. And now we use the equivalence that is given by the non-degeneracy of the Calabi-Yau condition, and we obtain maps then from A to C and from B to C, and induced induced. We view this as maps in of C bimodules. And if this square is co-Cartesian in mod CE, then we say that the cospan is n Calabiyau. So an example of this is the following. So I can start with any map F from A to B, so any map between DG categories. And then what you can define is an n Calabiyau completion. So beforehand of the map F. So beforehand we had n Calabiyau completions of objects. Now we have an n Calabiyau completion of a map. And this is defined as follows. We just take the free DG algebra of the B bimodule that you obtain if you take the inverse dualizing complex of A and you induce it up to a B module, B bimodule. Okay, so what does this give us? So if we have this amorphism between smooth DG categories F, then F yields a cospan between the Calabi-Yau completion of A and the Calabi-Yau completion of F and the Calabi-Yau completion of B. And this is actually the right functoriality for Calabi-Yau completions, because Calabi-Yau completions are not actually functorial in the sense one would like to. If I have a map from A to B, then taking the Calabi-Yau completion doesn't give me, I don't have a natural map from the Calabi-Yau completion of A to the Calabi-Yau completion of B, but I can map a map of DG categories between A and B to a cospan that has the property of being n Calabi-Yau. So that's the theorem below. So if I denote DG the homotopy category of smooth DG categories, and CY index n the homotopy category of n Calabi-Yau DG categories, with one morphism the Calabi-Yau cospans, then taking the DG the n Calabi-Yau completions is actually a functor. So what I haven't explained is if I take as one morphisms in this category CY the cospans, then how do I compose morphisms? That's not difficult to do. I just need to take a push out construction, and then I can actually compose this Calabi-Yau cospans and produce in this way new Calabi-Yau cospans. Okay, so let me move on to the last chapter of my talk. So now we have had this two parallel subjects. We have talked about n-shifted symplectic derived stacks, and we have talked about n Calabiyau completions of DG categories. And yeah, of course, one can wonder how are they related? And to obtain the connection, one uses a construction of Thorn and Vaquier. So what we look at, so this is the definition of Thorn and Vaquier. What we can do is if we have a DG category, then we can consider in the category of derived stacks, the moduli space of objects perf A of a DG category A. So here perf is bolded, which shows that, which in this notation means it's the derived, the derived stack, and not the DG category of perfect complexes, for instance. So how's this defined? As we said in chapter 2, like a derived stack is a functor from commutative differential graded algebras to spaces. And I just map a commutative differential graded algebra B to the maps in the category of DG categories, the maps from A, which is a DG category, to the DG category. So here is unbolded. So I mean the DG category of perfect B modules. So the sign here, the equivalence sign, indicates that I consider this as a space. So I discard all the one morphisms in here that are not equivalences. So the objects are, so the points of the space, what are the K points? The K points are just the isomorphism classes of perfect A modules. The B points, so a bit more general, a B point is a map from R spec B to perf A, where R spec B is the derived scheme that we have defined, are just given by, so every point, B point is given by an A B module M of X, so an A B bimodule that is perfect as a B module. We have very nice descriptions of the cotangent complexes in this case. So this has been also computed by Thor and Vaquier. If I look at the pullback of the cotangent space on the cotangent complex, the cotangent complex on perf A, then the pullback should be a complex, complex over R spec B, and it is given as the Helm space between M of A modules. Now we use just the A module structure between M of X and M of X, where M is the bimodule that defines X, shifted by 1. And by duality, we obtain that for the cotangent complex, we have a description by using now the fact that the dualizing complex is a Serre functor. So if we dualize, we obtain that the dualizing complex, that the cotangent complex pulled back is Helm of the inverse dualizing complex tensored with M of X, M of X, and now the shift of 1 becomes by the dualizing procedure a shift of -1. So that will be, it's a bit technical, but it will be important in a second. So what does this tell us when we look at this description and we take, for instance, A equal to perf K, or even A equal to K, just a DG category with 1 point and K as morphism space, then we know that the inverse dualizing complex is equivalent to A itself. So this means, as you can see, that the tangent complex and the cotangent complex just differ by a shift of 2. So we'll see later on that a perf K is indeed 2 shifted symplectic. So I have an isomorphism between the tangent complex of perf A and its cotangent complex shifted by 2. And we'll see how this can indeed be generalized. Last remark, well, the stack, of course, if I look at the DG category KQ, then I see that the usual stack of classical stack of representations of KQ with a fixed dimension vector is just an open substack in perf KQ. So it's indeed just it's a natural generalization of what it means to look at isomorphism classes of representations. Okay, so now the connection. So if so this is given by a theorem of Brav-Dickerhoff in 2018. So they show that if I start now with an n Calabiyau DG category, then I can associate to it a derived stack. And indeed, this derived stack, if A is n Calabiyau, will be 2 minus n shifted symplectic. And more generally, they show that if perf maps n Calabiyau cospans to 2 minus n Lagrangian correspondences. Okay, so a sketch of how to get from the Calabi-Yau structure to a shifted symplectic structure. So let's say we have a B point X. So B point is a map from spec B to perf A. Then I can first of all look at there's a functor from the there's a map between the Hochschild homology of A to the Hochschild homology of perf A. And there's a map to the one forms. So the one forms are the global section on the pullback here of the cotangent space of perf A, shifted by, I took them of degree 1 minus n, so degree 1 minus n forms. And this is equivalent by this description we just saw to Hom of the dualizing complex shifted by n, tensor with m of x, comma m of x, where m is the a-b bimodule that defines the point x. Okay, that is, I haven't explained at all what this single maps actually are, but what I can explain easily is actually what this composition is. So we have seen that a class in Hochschild homology of A is a map of A bimodules between the dualizing complex shifted by n and A. And so all I need to do is I tensor, I get an element in, yeah, that's not entirely correct what's written here, we'll fix this. I'll get an element in Hom A dualizing complex shifted by n, tensor with m of x, comma m of x, by just tensoring this map eta with m of x. So it's actually very simple to say what this map actually does, and it produces out of an n Calabiyau, not an n, but out of a morphism between the dualizing complex and shifted, and a one form. So to obtain a two form, I can just apply the differential, for instance, and we'll see that this is actually the right thing to do. Okay, let's sum up what we've seen so far. So what can we do? We have a DG category.
Sorry to interrupt.
So
We're very much to the end, so we should try to wrap up quickly.
Yeah. So I have 5 more minutes, no?
Well, according to the schedule, 0 more minutes, but you can take a couple more in order.
Sorry, I thought I had 5 more minutes. Yeah, I sum it up quickly. Yeah, okay, so we can go along the top. So if you take a DG category, you can produce a space out of it, and using the construction of taking the n 2 minus n shifted symplectic of taking the 2 minus n cotangent complex, you can produce a 2 minus n shifted symplectic structure. So this is what we've seen so far. We've also seen that if you have a DG category, you can go along the bottom. So you can first make it n Calabiyau. So this is the construction of Keller, and then you can apply perf to it, construction of Thorn-Bezzosi, and this will, by the theory of Dickerhoff and Graf, also give you a space that is 2 minus n shifted symplectic. And what we've shown with Bozec and Calaque is that the spaces are actually equivalent as 2 minus n shifted symplectic spaces. So they're not only equivalent as derived stacks, which was a no, but also their natural shifted symplectic structures are the same. The same is now true if you have a map of DG categories. Then perf is contravariant. You get a map between the stacks perf B and perf A. We've seen that out of such a map, any map of stacks from X to Y, you can produce a shifted Lagrangian correspondence. So this is what it looks like. And this shifted Lagrangian correspondence is actually exactly the same than if you apply perf to our co-span, n Calabiyau co-span condition. So this is what this says here. This is a generalization of the first result. Maybe I'll skip the case of the n Calabiyau. Well, I can just say we can do the same thing. We can make sense out of identify perf of deformed Calabiyau completion with what is called the critical locus, which is a pullback of the 0 section to the cotangent space and the graph of a 1 form. And to sum it all up, so we have a commutative, we have a natural isomorphism between going from the top, so this is taking Calabiyau completions and then perf, and then or applying first perf and then taking the 2 minus n shifted cotangent space. It's going along this square gives us an equivalence. And last thing I wanted to mention is that an application, so the application of this concrete application to this work is finding new Lagrangian subspaces in classical symplectical spaces, and this is what Tristan will talk about on Thursday. So let me stop here. Sorry for going over time.
Allow everyone to unmute themselves.
It's, yeah.
I have a question. Philosophically, is this Calabi-Yau completion, is that like purely non-commutative, or does that correspond to something more classically?
Well, I would say if I mean, now you can say that the Calabi-Yau completion, is what is in the commutative world, taking shifted cotangent spaces. So this
I
is
see, but you're taking the shifted cotangent space on classical.
Yeah, indeed.
I see. Cool. Thanks.
Hi, can I ask a question?
Sure.
Can you hear me?
Yes.
I'm trying a new microphone. I wanted to ask in your second to last slide, when you had the twisted Calabi-Yau completion, that's okay. The twisted Calabi-Yau completion, does anything special happen when the class itself is a Calabi-Yau structure?
When the class itself is a Calabiyau structure.
Yeah, the class in N-1.
I'm not sure. I'm not sure. Yeah, it's a good question. I'm not sure. Usually it's not, but yeah, I haven't computed any example in that direction yet.
Okay. Well, thank you. Thank you for your talk.
Ezra, go ahead. I just unmuted you. I saw you had a question.
Actually, my favorite example of a Lagrangian is in a paper of Huang and Polishchuk. And so I was wondering if that might fit this picture. It's, roughly speaking, it's the derived stack of graded vector bundles somehow inside the derived stack of perfect complexes.
Okay, and that's a Lagrangian. Yeah.
Well, it's actually coisotropic, but you can adjust it.
And it's. I mean, they're both derived stacks, and this is a zero-shifted Lagrangian.
Yeah, it's a. I can. If you haven't met it before, then I can send you a.
No, it's a paper of Polishchuk and
Huang.
Huang. Yeah, I will look it up. Thank you very much.
Yeah, it's very
That's interesting.
Yeah.
No, I didn't know at all about these examples. Yeah.
Oh, wow, sorry. Bernard is correcting it. Zhang Hua, yeah, I've got his name wrong. Sorry. I'll send you the, yeah.
Okay, thank you very much.
Svetlana, please go ahead.
Hi. Yeah, thank you. Thanks for the talk. I wanted to ask if there exists a relative setting of sorts that would like treat like elliptic fibrations, for example.
I don't know, actually. I mean, this is very recent work, actually. So we just put it on the archive. We haven't explored it yet. No, I don't know.
Thank you.
Yeah, I'm sorry.
Are there any other questions? Oh, I see.
I have one. At the end of section 3, there was a theorem which, if I understood correctly, stated that in the case of the free completion construction, you get a functor from DG categories to Calabi-Yau N categories with one morphisms given by cospans.
Yeah.
If we twist this whole construction or deform it by, like say in the quiver case, by adding a potential, do we get a similar result? Like,
yeah, in fact, it's also in our paper. I haven't talked about it, but there's a deformed version of it. Yeah. So the deformed version is when you add a potential that is non-zero. So yeah, that also works actually.
Thank you.
So you can define this G of F, you can define G of F comma C. So a deformed relative Calabi-Yau completion.
Sure, makes sense.
It's a little more complicated. That's why I haven't actually gone into it. Yeah.
Are there any other questions out there? Well, if not, let's thank Sarah again for this great talk.